Alright, ladies and gentlemen, let's talk about section 6.4, exponential growth and decay. Now, we'll begin just by making sure you understand that you have done exponential growth and decay before. In fact, you go all the way back to Algebra 1 and you were doing examples of exponential growth and decay, usually in talking about money. Today, we're going to expand that. We're going to talk about how exponential growth and decay is related to separable differential equations. And then we'll also tie that into continuously compounded interest and then modeling growth. What is a separable differential equation? If you have an equation that looks like this, dy dx equals f of y g of x. Now, all that really means is you've got two parts. One part defined by y, one part defined by an x. Then this fraction, or this problem, can be broken up to look like this. You can move your dx over here to be with the g of x. You can divide the f of y over here. And what you end up with then are two distinct sides. One side is being defined by y, one side is being defined by x. This is what we call separable differential equations. Now, just so you know, there are also non-separable differential equations. We will not get into that branch of calculus just yet. That will come later. Alright, solving by separation of variables. Alright, we look at this dy dx equals xy squared, and then we'll also, you'll notice, we have an initial condition here, so we'll actually get the c value at the end. Let's go ahead and take care of this square. Let's get rid of those parentheses, x squared, y squared. Now, we ask ourselves the question, what do I move around? Do I want to move the x over here to the y? And what do I move where? Well, I want to get the dx out of the bottom, and the only way to do that is to move it over here. But in doing so, I need to move the y squared over to this side to be with the dy. So we have this right here. I move the dx to the right, I move the y squared to the left. Notice when I move the y squared to the left, it did become y to the negative second. That's how you would divide. Now that I've got that, I will take the integral of both sides. Alright, now we'll use our anti-differentiation rules. If you add 1 to negative 2, you get negative 1, divided by the new number. Add 1 to 2, you get 3, divided by the new number, plus c. Now, certainly we do want to simplify this just a bit. That y to the negative 1 can be moved to the bottom, make it y to the first. Negative 1 over y equals x cubed over 3 plus c. Now let's find the c value. It tells us that x is 1 when y is 1. So I'll plug 1 in for x, 1 cubed is 1. I'll plug 1 in for y right here. And now we'll solve for c. Move the 1/3 over here, so negative 1 minus 1/3 is negative 4/3. Plug that c back in up here, so negative 1 over y equals x cubed over 3. And instead of plus c, I now have minus 4/3. This is a very simple example of a differentiable equation that you can solve by separation of variables. We actually can take it one step further. Forgot about that. I do want to point out, though, that if you were to leave the answer like this, it would be perfectly fine. But we can get a common denominator here, and we can reciprocate this. We can move the y to the top. We can move this to the top. And then notice, because of this negative, instead of x cubed minus 4, I move the negative over here, and it's 4 minus x cubed. Forgot about that simplification. But again, this answer here is perfectly acceptable. This answer here is perfectly acceptable. Both would work. Now, what does this have to do with exponential growth and decay? The law of exponential change says this: if y changes at a rate proportional to the amount present, in other words, if dy dt is equal to ky, so the amount of change that's going on is directly proportional to the amount that you have at any given time, this is exponential change. Now, what I would point out to you right here is that this is a differentiable equation that can be solved by separation of variables. Now, when you solve this, and you do a little simplification, you end up with this equation right here. Y equals y naught e to the kt. Remember, y naught, whenever you say naught, that means initial value. This should look very familiar. This is an equation that you've seen before many times. If the k is a positive value, it's growth. If it's a negative value, it's decay. Now, in a specific example of this, and we can skip past all this and go right down to here, a specific example of this is continuous compound growth. A of t equals a sub naught e to the RT. Perhaps you're used to seeing p's here. Or a, maybe an a right here and a p right here. A equals p e to the RT, the PERT equation. This equation is a specific example of this one where P would be a principal amount dealing specifically with money. But this is an example of compound continuous interest. The interest growth is not broken up into intervals. It rather grows continuously at a constant rate. Alright, some examples. Compound interest continuously. Suppose you have $800, 6.3% interest, and you're going to invest it for 8 years. What is going to be the price difference between a compound continuously situation versus one quarterly? Well, let's see. First of all, compound continuously, we have this. If you want to use a P there, so it's PERT, that's fine if that makes you more comfortable. All right, what do we have? What do we plug in? Well, I know that A sub naught, the starting amount is 800. The percent, 6.3%, can be written as 0.063. And the time is 8 years. Make sure you're careful plugging that into your calculator. And you get 13, 24, 26. Now what about compounded quarterly? Well, I can't use compounded quarterly because it's not continuous. So I have a different equation, and it's this equation here. Perhaps you again remember that from Algebra 1. A sub naught, starting amount, 1 plus R over N, R being the rate, N is the number of times compounded per year, raised to the NT power, T is time. So what do we know? Well, again, we know 800 is A sub naught. We know the rate R, 6.3, change it to a decimal. N, how many times a year is quarterly? N would be 4. And then again, T is 8 years. I plug all that in, looks like this. And then punch that into your calculator. And again, be very careful. It should handle all that okay, but be very careful that you punch it in correctly. And 13/19/07. So you see, after 8 years, it's really not much of a $5 difference. But, you know, again, $5 is $5. Why not get the most as we can? Alright, example 3, finding half-life. Find the half-life of a radioactive substance with decay equation y equals y naught e to the negative kt. Remember, this was our general exponential growth decay equation, negative k for decay. And show that the half-life depends only on k. In other words, the half-life of a substance depends only on its rate of decay. It depends on no other factors. So we'll start with y equals y naught e to the negative kt. Now, if I'm talking about half-life, what I'm talking about is the amount of time it takes for the original amount to decrease to half its starting point. So if I start with y naught after the half-life goes, then what I have left is 1/2 y naught. See, again, it's half the starting amount. I can divide both sides by y naught, and we end up with this, 1/2 equals e to the negative kt. And now your job is to solve for t. I'm going to solve for t. Well, first of all, I need to get rid of the e. So we'll take natural log of both sides. Natural log 1/2 equals negative kt. Just eliminate the e on the right side. And now I'll divide both sides by negative k. And then I could simplify this just a bit. Remember, 1/2 can be written as 2 to the negative 1. And that negative 1 on the 2 can be brought out front. And that's why we have a positive now, natural log 2 over k. And you see, then, the half-life t does only depend on k, because natural log 2 is a constant. So there are no other factors that play into the half-life of an object. And that is a formula that maybe you'll want to remember in the future, natural log 2 over k. We'll use it some, not a whole lot. The formulas that we have previously really take care of the half-life for us. We may use it from time to time. Alright, let's do an exponential growth and decay problem. Population. Beginning of the summer, population of a hive of hornets. We hate hornets. Growing at a rate proportional to the population. That means exponential growth and decay. From a population of 10 on May 1st, the number grows to 50 in 30 days. If the growth continues in this same model, how many days after May 1st will the population reach 100? Alright, we'll begin with our model a sub naught e to the kt. Or if you want to use the other one, y equals y naught e to the kt. It all works out the same. Well, the first thing we need to do is we need to find the k value. We need to determine the constant of growth. But we've got enough information to do that. I know the starting amount is 10. And I know that after 30 days I have 50. Starting amount is 10, and after 30 days, I now have 50. So now I can solve for k. Divide both sides by 10. I'll take the natural log of both sides to eliminate the e. And then I can divide both sides by 30, and there's my k value. Natural log 5, all divided by 30. Now, if you would prefer to write that as a decimal, that's perfectly fine. I'm going to leave it in an exact form as we go, but if you want to make it a decimal, no problem. Go ahead and do so. So let's take that and let's plug it back into the equation right here. Now the problem says, how many days is it going to take to reach 100? So I'll go back to my original starting amount of 10, and now this time I want to reach 100. Now, instead of solving for t, we'll solve for k. I'm sorry, the other way around. Instead of solving for k, we'll solve for t this time. So we'll divide both sides by 10. We'll take the natural log of both sides. That gets rid of the e. And then we multiply by the reciprocal 30 over natural log 5. And we end up with all this mess, which means absolutely nothing in a real-world scenario. Decimal approximation of that gives us nearly 43 days. So if it takes 30 days to grow to 50, it will take nearly 43 days to grow to 100. Now you say, well, why isn't it just 60? Because if it's 30 to go to 50, it should be 60 to go to 100. Well, you're assuming a linear growth in that point. Remember that in exponential growth and decay, the rate at which you grow depends on how many you have. So when you have 10, the rate at which you're growing is not near as fast as when you have 50, and that's not near as fast as what you have when you're approaching the 100 mark. Now, carbon-14 dating. Scientists who use carbon-14 dating know that it has a 5,700-year half-life. Find the age of a sample if 10% of the radioactive nucleus originally present has decayed. So not 10% left, but 10% has decayed. How long then has it, how old is it? Again, we'll start with the same equation. I like this equation. It's easy to work with. I'll use it a bunch of times. Let's find the k value. 0.5 A naught equals A naught e to the k 5700. Now, I will tell you that you could, instead of doing what I'm doing now, you could go back and use that natural log 2 over k equals t being 5700 in this case. That would also work. I'm just so used to using this formula, I go back to it every time. But if you want to use that other one, go right ahead. Divide both sides by A naught. And here we have the half-life, 0.5 e k 5700. Natural log, both sides, divide by 5700. And there's our half-life. Now, if we continue on, we'll take this, we'll plug it in. Right here, there's our new k value. Now that we've got this plugged in, let's simplify it just a bit. Skipped around just a little bit if you notice the screen jump some. Let's simplify this just a bit to make life easy on ourselves. I'll pull out the natural log of 0.5. We can then take the e and the natural log, they'll cancel out, and so I just have 0.5 right here, or 1/2 t over 5700. This is another form of a half-life formula that you might see at some point or another. Now again, I only want 10% to have decayed, so if that is the case, notice that I have 90% left, or 0.9. Now we solve for t. I took the natural log of both sides, although with your TI spires you can do the log base 1/2 if you wish, it doesn't matter. And then I'll divide by the natural log of 1/2. I'll multiply by 5700, and then you'll want to put all that into your calculator, 866 years. Now, we are about at the end of this first 15-minute video, so I'm going to go ahead and stop it here, and then we'll start the next one here in just a moment.